Hey Royals, in today's lesson we're going to investigate gravitational potential energy a little bit further. So in a previous lesson we defined potential energies as a form of stored energy or energy based off of a location. Now if I was going to lift this little Scottish man up into the air, I'm increasing his ability to do work, otherwise known as increasing his energy that he has stored in him. So we understand that if I were to lift an object off the ground, it has the ability to move. However, if it was sitting straight on my hand and I let go of it, no, it doesn't move, right? So let's figure out algebraically how I represent how much energy an object has based off of its location relative to a reference point. Okay, so if I was lifting an object like my little Scottish man up into the air, I'm doing work on that object. And we know that work can be represented as the force applied on the object, so I'll call it FA, multiplied by the displacement and the cosine between the two, between the force vector and the displacement vector. So if I'm lifting an object up in the air, my force that I'm applying on it is acting straight upwards. And my displacement is also going to be straight upwards since I'm lifting the object up. The angle between these two vectors will be 0 degrees. And if you put 0 degrees into your cosine function, you'll find out that it gives you 1, which means by lifting an object straight up in the air and I'm applying a force in that direction, I'm doing the maximum amount of work onto my system. Now, if I lift this object into the air, the force I must apply to it has to be equal to the force of gravity pulling this object straight downwards, which means that the applied force that I put onto my Scottish man here has to be equal to the force of gravity that is attracting this object towards the center of our Earth. And we know that the force of gravity can be represented as mg, which means the mass multiplied by the gravitational field intensity. So that's telling me that the applied force can be written as the mass multiplied by little g. Okay, so putting this all together, I say that the work is going to be equal to, instead of writing FA, I'm going to write mg multiplied by delta d. And now I'm not going to write cosine theta anymore because we know that comes out to 1. However, if I'm lifting the object straight up in the air, there's no point of calling that displacement delta d when we know it is actually just a change in height. So instead of writing delta d, I can write this as the work is equal to the mass of the object multiplied by the gravitational field intensity multiplied by the change in height. So we know from the work energy theorem that the work done on the object is equal to its change in energy. And in this case, this change in energy is based on gravitational. So the work done on this object is equal to the change in gravitational potential energy. So instead of writing W, I'll write delta E subscript G is equal to mg delta H. And so there's our equation for change in gravitational potential energy. And that equation shows up on your formula sheet. So this is based off of a change in height. If we define a reference point, we can say that the height that an object has is based off of a reference height of 0. So we can say that a energy that's stored in an object is equal to, so Eg is equal to the mass of the object multiplied by g multiplied by its height. So it's a function of height in this case. And so how I went from that previous equation to this new equation was the fact that I talked about the change relative to a height that I'm going to define as 0. So in the picture here on our right hand side of our page, if I say that the ground has 0 height, that's what I'm saying, that if the object were to sit on the surface, it's not going to move once I remove my hand from holding it, right? So in this case, imagine the bottom hand here is the ground. So as long as this Scottish man stays there, he's not going to move, right? So if I'm looking at this situation, I say I'm moving from this equation down. it's going to be change in height, means that it's a final gravitational potential energy minus its initial gravitational potential energy is equal to its mass multiplied by its gravitational intensity, h2 minus mgh1, final height minus its initial height. And if I call its initial height 0, that means that this whole term is equal to 0. And by definition, I'm going to say that the energy at that position is 0, which means that my equation becomes Eg2 is equal to mgh2. So it's telling me that the energy that's stored in the object based off of height is equal to the product of the mass multiplied by gravity multiplied by the height at which the object is above my reference point. Okay, so this is an introduction to gravitational potential energy, and we came up with an equation that can be used to calculate how much energy an object has stored in it based off of its height. So if you have any questions or concerns, please don't hesitate to reach out to me. I would love to answer them.